All right, everyone, welcome back to the Food Safety Extension Workshop. It's my pleasure to moderate this session on process preventative controls for food products. I'd like to welcome our presenter, Dr. Cangliang Shen. Dr. Shen is an associate professor and extension specialist in the Division of Animal and Nutrition Sciences at West Virginia University. His research interest is in developing post-harvest sanitizing procedures for reducing food safety risk on poultry meat products. Dr. Shen serves the International Association for Food Protection and Institute of Food Technology in various leadership roles. As a reminder, just like all the other sessions, please feel free to put your questions into the question box on your panel. And with that, I will pass it over to you, Dr. Shen.
Thank you very much, Caitlin, for the introduction. So let me just share in the slides. This is the first one, is disclosure of the conflict of interest. I don't have anything, and this talk did the response supported by the USDA NIFA and the Critical Agriculture Research Extension Program and the Education Workforce Development Program for the undergraduate research and extension. Before we talk about the FSMA process preventive control, I would love to talk a little bit about the history. So this is what happens for the HACCP, Hazard Analysis Critical Control Points. What it comes from? This is in late 1950s. So by the time, we want to make sure the food is safe in the space. So the Fewsbury Company come out with this HACCP concept. It is a very proactive approach to make sure the food in the space is safe. And it's not 100% guarantee food safety, but it is a proactive action. Basically, is to control the biological, chemical, and the physical hazards. And why has a plan today become a hot topic? Because of this outbreak. Everybody knows this is back in 1993, almost 30 years ago, in Jack in Box in Seattle, which is an E. coli 0157H7 contaminated hamburg, which is caused 171 people hospitalization, including 45 children. And 28 of them suffered from the kidney problems because 0157H7 will cause hemorrhagic uremic syndrome. And more badly happens is 4 children are died. So that's why it touched the nerve of the White House by the time. And the time is President Bill Clinton and the Vice President Al Gore try to work with the Congress to have the HACCP plan. Now, at the same time, the USDA, United States Department of Agriculture, Food Safety Inspection Service, also come out with cooking guidance to successfully destroy E. coli 0157H7, which require to cooking the internal temperature to 160 degrees Fahrenheit, which is 71.1 degrees Celsius. Now, be careful here. This means the internal temperature. It is not the surface, which means the geometrical center temperature has to be 160 degrees Fahrenheit. Therefore, a couple of years later, I believe in 1996, the Federal Register published this 300-page documentation, which is talk about HACCP. Therefore, it comes out with, everybody knows, the 7 principles of the HACCP, including conduct a hazard analysis, determine critical control points, establish critical limits, establish monitoring procedures, establish corrective actions, verification procedures, and finally, very important, the record keeping and the documentation procedures. Now, something I would point it out that although the HACCP coming from is E. coli 0157H7, this pathogen reduction documents is talk about the salmonella reduction, and they are using the surrogate, which is E. coli biotype 1. So kind of not really consistent with the origination. However, this did become a law in the United States. Now, meat poultry establishments, they all need to have the HACCP plan. Of course, they have a different timeline for them to to establish this hazard plan in their own plants based on their amount of the saline every year. Now, these days, you can go to FSIS website, Food Safety Inspection Service website. You can see a different module. Most of them are meat products. And they also have egg products, catfish, and other things, maybe juice, I believe it has it. However, if you notice the hazard model, they did not cover one of the major products, which is fresh produce. Because we always think fresh produce is safe. And until this happens, in 2006, Salinas, California, Central Valley, this is a big places for generate produce in the United States, including Taylor Farms, Fresh Express, Dow, all three major companies. This outbreaks happens is the first time E. coli 0157H7 find in packaged spinach, and it caused 199 persons, 26 states, and finally there 3 deaths happened. Continually after this, 6 years later in Colorado, and there is another big outbreak, which is a cantaloupe. Listeria monocytogenes, contaminated cantaloupe, also resulted 33 associated deaths. And very ironically, the Jason Farms passed the third-party validation just a week before the outbreaks happened, and their score is A+, which is 95 among 100. And the people go to the plant, do the inspection, find that they did a horrible job of the cleaning and the sanitation. Now, because of these 2 major outbreaks, really, people think something you need to do for the fresh produce. Therefore, kind of generate this idea, which is about the FSMA, although FSMA is a very comprehensive food safety regulation. So FSMA, the full name is Food Safety Modernization Act, signed by President Barack Obama in 2011 into the law. And there are major 7 rules we listed here. However, for our food safety person, we really care about is the first 2, which is preventive control rules for human and animal and the produce safety law. For others, it's most likely is a trade market or those other things. So this keeps all the extension specialists in the university, especially 8062 land-grant university, are very busy in the last 10 years to generate all kinds of the education outreach documents for the produce processors, meat producers, all kinds of producers, especially small to very small producers, to make sure they follow this regulation. Now, HACCP, it is many years, and FSMA, especially the preventive control procedure, which is adopted as the HACCP concept. However, they did some modification and add something there, especially they are including broad-based control, not only process preventive control, they including sanitation preventive control. When sanitation control is a potential hazard. Allergen preventive controls, I mark red here because I always think this is new for the FSMA. Supply chain preventive control, and also the final, you have a recall plan. Talking about recall, most likely we talk about 3 levels. If you have a foodborne pathogen outbreaks, that's a recall class 1. And if you have allergen, originally it is a recall plan 2, type 2 recall plan, and the mislabel usually it's a class 3 recall level. But a recall plan has to be very well documented in these preventive control procedures. And every procedure, you need to have documentations. You need to establish criteria, limits, monitoring procedures, corrective actions, very important for verification, and the record keeping documentation. So if you look at the overall picture, what is FSMA preventive control really talk about is based on the hazard analysis. And I believe previous speaker already talked about then you need to come out with full control and then including a recall plan. So today I will talk about is this heavy menu on chapter 9 called talk about process control. So this is what we're going to talk about today is process preventive control, including 3 major items. The first one, critical limits. Second one, monitoring procedures, focusing on target for critical control points. And last one, corrective actions. Validation, verification, record keeping, all those will be covered in chapter 13, 14, 15, I believe later on. But we're not going to cover them today. The slides of this chapter has not been including critical control points. So I would love to introduce a little bit. That means a step or a point or a procedure during the food processing could be effectively to eliminate or reduce food safety hazards to an acceptable level. So some food safety hazards need to be completely eliminated. For example, E. coli 0157H7 in ground beef is 0 tolerance. Sometimes it is just reduced to an acceptable level by the regulation. For example, salmonella on the poultry meats, it is allowed you to have up to 7.5%, and the Campylobacter could be up to 10.5%. So that means you're going to reduce it to reach to a level which is approved by the federal regulation. This is what we're going to film today to cover this one, but not everything. This is usually is an example for black process control form should be well documented in your food safety plan. You need encoding, very important at the beginning, you need to have those product name, address, issue date, and also the supersized date. You need encoding process control, hazards, critical limits, monitoring procedures, corrective actions, verification, and recording. And we often the time to see those lots of the small producers, they cover everything very detailed, but sometimes they miss the date or miss the product name even. So those are important to completely well documented. Sorry, that's stuck again. Wait a second, it's okay. So the next slides, which is talk about, give you an example of this table. This table, which is just a template you could use. So here they pointed out a critical control points, which is a cooking process, and the hazards, which is a salmonella. Now, we want to mention a little bit about this vegetative pathogen. What means a vegetative pathogen? Usually, it's a normal bacteria grow in the food products in the liquid solution, but it is not, we are talking about something on the food contact surfaces. In contrast to vegetative pathogen, we have another terminology for that is for biofilms. So these documents usually is for the example is for vegetative pathogen, is not for biofilm, because the biofilm will cause resistance to the antimicrobials. So if you're talking about to control the biofilm model for the contact surfaces, then there will be a different story. So here what we focus on is vegetative pathogen such as salmonella. Now you see here, you have justify your decisions roughly cooking. And what's the prevention we should use is cooking to achieving a lesser temperature. So we want to talk about the next is critical limits. This is encoding the definition of critical limits, how we determine critical limits, the relationship between critical limits and operational limits. Operational limits is a more conservative value compared to critical limits. And then, of course, we have to gradually fuse the process control form. So first of all, what is critical limit? I would say that this is target for critical control points. It is a value. It is a minimum or maximum minimal value or a combination of value for a biological, chemical, physical parameter to make sure the critical control points is well under control to minimize or prevent a hazard. This definition coming from 21 CFR. CFR stands for Code for Federal Register. Now, I would add something to here is this value has to be measurable, observable, and achievable, which means you could see it, you can measure it. It's not something just come out of your mind. If you cannot achieve it, then that should not be a value you used. Now, another thing also I want to mention, although here I mentioned about the biological parameter, but until today, biological parameter has not been encoded in microbiology data. Now, with more and more rapid testing methods developed, I'm optimistic this something could be changed in the next 5–10 years. However, recently, until today, the biological parameter is not encoding microbial data, which means the microbiology population is not will be the parameter yet. Another thing is that critical limits in the FISMA in this process preventive control is allow you to have a range. However, in the old HACCP documentation, they will have to be a fixed number, is not a range. So when we're going to get these critical limits, it could come from federal regulations, from FDA. For example, they have a food code. They have a pasteurized milk ordinance, acidified foods regulations. They could come from the local documents, state regulations. For example, USDA regulation basically coming from Food Safety Inspection Service, FSIS. That could come from university food scientists, microbiologists, some consultants, trade associations, or even some equipment manufacturers, which means some expertise. That also could come from some of the previous validated study. It could be an in-house experiments or could be a third-party challenge studies. So before I joined the university academic area, I work in a company which is called IEH Consulting Group in Seattle. My older employee, most of the time they do, part of their work to do is a validation study for lots of the small companies. So those are the resource for critical limits. Last thing, it could even come from peer review publications, but I have to point it out that lots of us coming from university or graduated, new graduated from university, and we did lots of the research by ourselves. We read papers, we write papers. So our first impression is that peer review publication is a good resource. However, we have to be cautious that in the real life, the real processing line, it is completely different from the lab. So when we use those journal publications, we have to be careful to see is that our processing condition really fits those lab conditions. So I give you a very easy example. Most of the D value or the value coming from the cooking study is for a grounded beef, which is sometimes 3 to 5 grams in a circulated water bath. But in the real life, most of the time we are cooking a big steaks in an oven or in the grill. So the numbers maybe not match each other. Another thing is that the fat components, if the paper has been using knuckle, which is only like 5% of fat, however, you are using chunk during your processing meat. The chunk have like 25% of the fat. The fat will be dramatically impact the thermal inactivation of the pathogen because it will protect the pathogen during the thermal processing. So by that means, the manuscript may not be worked for your situation. So that's why for these slides, the scientific literature usually is at the bottom. Obviously, critical limit has to be met, because if it's not met, which means the deviation could be happen. A hazard is not necessary control. The safety of the product is in question. That's why the critical limits has to be achievable. And we also need to give a lots of options sometimes, not only one or two fixed conditions. That's why we need a variety of options. And we also need to be based on our processing line to establish the critical limits, which is practically. So I'll give you some of the examples. Here are some examples for the critical limit. So for example, you will see on the top, you will see some of the battered product. Staphylococcus aureus is a hazard, critical control points, batter application. Now, critical limit example, they have two. So you could do is not exceeding 10 degrees Celsius for more than 12 hours, or you could increase the temperature to 21 degrees Celsius for more than 3 hours. However, if you use two different critical limits, these has to be pre-validated, even verified by the third party before you do it. And then another example, chopped product, metal detection. We're using metal detector, make sure it's always on. No detectable metal in the finished products, or we can do the knife bladers are intact after each run. Another example here, this is only one critical limit here, is for the high water activity ready to eat foods. That's make sure the core is less than 41 degrees Fahrenheit, which is 5 degrees Celsius. Next one, for the ready to eat meat products, Listeria monocytogenes, cooking is the critical control points and the critical limit. Make sure internal temperature 160 degrees Fahrenheit and the holding time 1.5 minutes. Now here you see another products, which is gives you example, the dried product have a multiple conditions, and these conditions had to be previously verified. Okay, the last one, Clostridium botulinum in the pickle foods. This is always a hot topic because we talk about the pickle foods. Their water activity is around 0.85, pH 4.6, so we call it a low acid foods. Now you see all these conditions, including the product weight, soak time, how much acetic acid we're going to add, but the idea is to achieve the maximum pH is 4.6. Now, lots of the time, we even set up the pH a little bit lower, like 4.4. Even in my state, in West Virginia, we set up pH like 4.0. That is called operational limits. We're going to mention this real quick later. And the next one, okay, so that's, okay, here's some example for different options. Frozen omelet, everybody likes omelet. Okay, it's made by egg with some cheese. So what's the hazard? Salmonella, critical limits, critical control points, cooking, critical limits. Make sure the internal temperature 70 degrees Celsius. Here is the option is individual cook, batch process, you cooking in a pan oven. However, we have to realize that frozen omelet, during the cooking, they can be thawed, and the morphology could be changed. So it is difficult to test in each individual omelet their internal temperature. So what you have to do, you have to sometimes not really measure each individual internal temperature. You're going to have other critical limits. It is a combination, including the oven temperature, belt speed, and how many batter volume you need added. So this is a combination with the critical limits. And these three conditions has to be previously validated. So here it gives you two choices for the critical limits, how you're going to achieve it. So we're going to fill this form. We talk about hazards, process control, hazards, critical limits. Then therefore we next move on to the monitoring procedures. Okay, monitoring procedures, it's a food safety principle. We will talk about definition of the monitoring procedure, why it is important, what's the purpose, how we design a monitoring system, how we should do, what kind of the methods and equipment for monitoring critical limits. So first of all, what is the monitoring definition? The monitoring means a planned sequence of observation or measurements to assess whether control measures are operating as intended. And I'll also add something there, at a specific frequency. So what are the purpose for the monitoring procedures? Monitoring procedures, we need to make sure the critical limits is met, because otherwise we'll trigger some process adjustment. We also need to see whether or when there is a loss of the control, which means a deviation happened. Because deviation happens, we have to trigger the corrective actions. Last thing, we need to do a very good job of the writing, which means the recording, to make sure the process is under control. Now, here is a key thing, what we should monitor, how we should monitor, how often we should monitor, which means the frequency, and who we should monitor. Is that always the supervisor should monitor? Does not necessarily. Sometimes lines pressing is better than that. So we will talk about a little bit. What we will be monitoring? Obviously, like we just mentioned, those things you could be achievable, you could be measurable. So for example, temperature. Cooler, you need to make sure the temperature you are monitoring, it's working. It's controlled at 5 degrees Celsius. The thermometer is good. The time is good. The volume, weight added into the products is reasonable. And the line speed flow rate, these usually is a combined conditions. How many acid we need added into a pickle samples to make sure the pH is lower than 4.6? And what activity? For low acid foods, what activity is important? And chemical concentrations. For example, if you are using peroxyacetic acids, you need to make sure that is below 96 ppm. And you need to make sure that concentration is reached. Appearance, performance, process performance. Now, they talk about many others. This is also included, the metal detector is on, the sizing bar is on, to make sure is oversize will be rejected. Now, how we should monitoring? Obviously, the first thing is calibration. So the person who is doing the monitoring, they definitely need to know how to do the calibration of thermometer, pH meter, and the charter recorder. Now, often the time when we go to see the small processor, we know that the pH meter, the calibration have a 3 buffer, pH 4, pH 7, pH 12. Now, lots of the small processors, they only do is pH 7. Whenever you they touch the sample, they see the pH 7, that's good. They use their preliminary prepared liquid. So you have to tell them that's not good, because you have to also do the calibration of those other 2 values. We always like inline analyzer and a real-time analyzer, but not always will real-time. So sometimes it delay a little bit, it's fine as long as your product is still online. So delay a couple of seconds, couple of minutes, that's necessary, that's reasonable. Now, last thing, sometimes we have to do visual checks. For example, detector, the metal detector is on, the sizing bar is on. And another good example is sodium nitrite. We added into the curing meats, let's say adding the hot dogs. We have to make sure it is below 50 parts per million. How do you make sure it is? We're using the double vision check to do it. So visual checks is also one of the components you can do, how the monitoring conducted. Now, continuously monitoring, we always like it. For example, I have a thermometer, I have a laser thermometer, or I have a thermocouple, could insert into the internal of the frozen omelet. We always could test in temperature every 5-10 seconds. That's good. In the produced wash water, we have an inline pH probe, can test in pH value all the time. That's good. We have a barcode scanning. We can do the barcode scanning very, very easily. That's very nice. However, always remember, periodically human involvement is necessary. So you are doing the thermocouple measuring the temperature. You may need to take a couple of the samples using laser thermometer to manually check it. You may need to get a cup of water, produce water from the washing line to measure the pH by yourself. And sometimes we do that at the beginning of the shift, at the end of the shift, once or twice at the middle of the shift. So that's important. Continuous monitoring is preferred, but always remember the human involvement is necessary. Now, non-continuously monitoring considerations is possible because it's not always there, the technology. Therefore, we need to determine how often we do the non-continuous monitoring. Is the process normally have a large variation? If it's too much variation, then the non-continuous monitoring has to do very often, very much often. Close a normal value to the critical limits. If your critical limits is 71 degrees Celsius, and my normal value is always 71.1 degrees Celsius, then you have to check more often. How much product is at risk? Well, if lots of the products you expected is at risk, then more often non-continuous monitoring is needed. So here are some of the examples. If it's a batch during making those like an omelet or those products, it's difficult to do the continuous monitoring temperature because it's flowed. So we have to do the temperature checks at specific intervals, beginning and the middle of the shifts. Batch process water activity checks. So everybody working in the labs, they know water activity. They currently do not have an inline continuously monitoring condition. You need to prepare the standard curve. Then you have a cup to put the sample there, then close the vessel, touch the spring, and then you see the value. Then finally it will be beeping. It took about 15 minutes sometimes. So it's a non-continuous monitoring. Last example, antimicrobial chemicals in the produced wash water. So for example, I need to testing how many perioxyacetic acids, PAA, add into the fresh produced water. There is no online like an instant message to do. So what are we going to have to do? We have to using titration methods, plus using the color spectrometer. And at that moment, we have to take times. It's sometimes, depending on your techniques, the titration technology, it could be 5 minutes, 10 minutes, even longer than that. But at the same time, you need to make sure your processing products is still online or not going to the commercial site until this testing is finished. Okay, so this is a non-continuous monitoring. Exception records. This sounds very, the terminology sounds like not very easy to understand, but I give you an example, you know. So over the weekend, if we go to buy a grocery, we have a very busy week next week. I'm going to buy a lot of the foods. So I go home, then I open my refrigerator, and I'm put all the foods there. Then I go back to my car trunk. I get another batch of the foods what I just bought. Then what happened? The refrigerator started beeping because the automatic temperature alarming is on. That is exceptional records. They based on is usually the automatic alarming system. So if you have an exceptional record system, you do not have to document it in the monitoring system. However, that exceptional record system must be pre-validated. It works. Who will do the monitoring? Obviously, a trained designated employee. Now, we always have an impression. Quality assurance person should do it. And a supervisor should do it, but that's not necessary. Because the supervisor, lots of the time, has to accompany with the inspection personnel. So they cannot always be there. And they may not be very familiar with the process or those details compared to the line person. So usually the line person will be better for the monitoring as long as he or she has been trained. And another thing is that usually we do the verification procedure, verifying the records. There's a person to do that. The monitoring person has to be a different person than that. But it really depends on the company. Lots of the small company, the verification person and the monitor person may be the same thing. So maybe the same person. So that's really depends on the scale of the company. Qualifications of the monitoring individuals, and we just mentioned, the person has to be trained. I usually recommend my students go work at the entry level in a local company, get a certification from Pennsylvania State University. Dr. Cassie Carter has a very good program. We need to get trained. Even myself, listening her lectures and get training myself like 10 years ago. And we need to understand the importance of the monitoring, because if the monitoring did not do very well, which means the critical control point is not under control, that means the hazard products could be generated. Now, we also need to understand the actions have to be taken when the deviation happens. You need to do immediate corrective actions, and we also need to do timely report deviation for some other actions. So, by all means say, these monitoring individuals need to have a very good food safety culture in his or her mind. So there's need to have a training. So this is what we have here, is filling the table. What are we going to do? What's the monitoring? Omelette temperature, 158 degrees Fahrenheit, 70 degrees Celsius. How are we going to do? Here the example is using infrared surface thermometer. But this has to be careful because this is a surface, it's not internal. Hot frequency, each cook station 4 times per shift, every 2 to 3 hours. What's a person going to do? The quality assurance technician or designated or line person. This is an example which is talk about hazards, parameter, critical limits, how, who, frequency we're going to do, and the corrective actions. So this is another example for you to using if you are working in the company to have these type of documents. Next one, corrective actions and the corrections. So we want to talk about the corrective actions and the corrections. The procedures for corrective actions and the recorded keeping requirements for the corrective actions. So first of all, what is corrective actions? That the procedures must be taken if preventive controls are not properly implemented. So which means the failure will be happen. Now, what is the definition of correction? It's a long sentence. I'm not going to read them word by word. What's the difference? Corrections, usually it's a minor issue. For example, in the morning, you're walking into the plant. You're trying to processing ground beef. And you see your cutting board is not sanitized. So you tell everybody, gentlemen, please stop. We need to do the cleaning and the sanitation first. Because otherwise, coliforms, generic E. coli, metal could be detected. The products could become adulterant. So those are the minor or simplest way to fix called correction. But you have to be careful. The correction cannot always happen. If it's always happen, then for the safety plan, you may have to reevaluate it. So that's some difference between corrective actions and the corrections. Corrections, they must be taken when process preventive control are not properly implemented, which means a deviation happens. Because deviation happens, the unsafe product will be produced or may have been produced. So for example, you set cook to internal temperature 71.1 degrees Celsius. And you using thermometer to do the monitoring, you find it's only go 70 degrees Celsius, which means the left already produced sample may have contaminated with E. coli 0157H7. At this moment, we need to analyze the nature of the hazards. How we should do it? It may be sometimes only a limited adjustment could be fixed, or sometimes need to do the reevaluation. It really depends on the nature of the hazard. Written documents you needed. You need to make sure is the problem is identified. and is implemented which means you have to treat it immediately. We also need to make sure it is not happened again, not reoccurring. This is hard sometimes. We need to evaluate the affected foods. Are they safe? At least they have to hold on temporarily, not go to the commercial markets. Because if the food already go to the commercial markets, that could be cause a public issue. And then you have to initiate the recall plan. So that's a completely different story. Okay. And we also going to talk about how we're going to treat the products. It does not mean they always need to be thrown them away. So we will talk about that. Corrective actions examples. There are some of the examples here. Immediately adjustment of process. I would say this, you could do it. However, it should not have lots of the tweaking. So what this means, I give you an example. We often see your printer. Let's say you have a thermometer cutter, you have a printer. Today the printer, you find it doesn't work very well. So you didn't change the cartridge, you shake a little bit. The ink goes back and it could have printed another 10 pages. If you only have like 3 samples left, you can do it. However, you cannot do it all the time. You can just shake the printer all the time to make but without changing a new cartridge. So this is immediate adjustment is okay. However, too much tweaking is not good. And you should have a power to tell the employee, please stop the line. And we need to see what the deviation happens. Sometimes we can apply alternative process. So for example, we are set at 170 degrees Celsius for cooking 5 minutes. And I find that today is only 165 degrees Celsius. So the low temperature, we may have to cook a little bit longer time. We call it online reprocessing. However, you need to make sure this online reprocessing condition is previously validated. Now, often the time, what we see is we have to repair equipment. We have to retrain the employees. This means you need to go back to see you for the safety plan, and we also need to evaluate the operation. Last, how are we going to treat the products? Obviously, we have to hold on. So at this moment, if the time is permit, the rapid testing of microbiology sampling is okay. However, that needs to be done in a really strict time limit. We need to evaluate the product, how we should do. You may need to deposition it. But how are you going to deposition it? Does not mean you have to destroy it. I want to tell you one thing. 70% of the United States ready-to-eat meat, like hot dogs, is coming from adulterated ground beef, which means the beef could be potentially contaminated with E. coli 015-7H7. So what they do, they have to fully cook to ready-to-eat meat. So that is allowed to do. Another way they do is make it become pet foods. But of course, you need to have another external connection. They couldn't make those become pet foods. So that's not always a choice. So what I'm saying here is that does not mean you have to be deposition or just throw them away. And they have other methods you can do. Sometimes you can make them as a casing even. So, but not an edible casing. So there are some other choices, but those have to be previously documented or evaluated. Unanticipated problems. This is always happen during the processing, which means your preventive control not properly implemented. It's not established. All of a sudden, something happened. You will find that one or more preventive controls are ineffective. Then you need to see the record. You sometimes see the record is incomplete. And you sometimes see the activities is not following for the safety plan, and the corrective actions are not appropriate. That means for the safety plan, you have to reevaluate it. So what we should do, you have to identify and the corrective and implementation problem. Same thing, you need to reduce the reoccurring. You need to evaluate all implicated product. Is that safe? Prevent adulterate and mislabeled products go to the commercial. Now, how we should reevaluate food safety plan is not going to be covered today because the chapter 13, verification validation procedure in this whole menu will talk about the detail. And I hope I have a chance later we could talk, sometimes later we could talk about that details, re-analysis of the food safety plan. Corrective actions require records. The actions taken to identify and correct the problem. When we took it, how we took it, we all need to reduce the likelihood that will be re-happen. We need to safely evaluate all the affected products. And the last thing, very important, recording and documented those products are appropriately treated or not going to the commercial markets. So this is a corrective action form. And you can see here encoding a very detailed information, date of record, lot number, date, time, the problem happens, description of the problem, root cause, actions to taking, person to take care of, amount of the products involved, how are we going to do the evaluation, final deposition of the product, very important. I saw lots of the small company, everything they filled up here, they did not have a signature who did it. Or maybe the same person who is a quality assurance person and also a verification person, but you have to have a name initial here, and very important, the date. Sometimes we even put like a temperature and weather here. More or less, we put some more information there. But I see people who did very good from the beginning to the end, but without signature. That's not really nice. Last one, we want to talk about operation limit. What is that? Operational limit, which is originally come from, is 2011, the National Seafood Hazard Plan. This means you have a more conservative value compared to the critical limits to reduce the risk of a deviation. So sometimes it is a quality reason. So, for example, sometimes the critical limits is 71 degrees Celsius. You find your products cooked to 72 degrees Celsius is good for the quality. You can do that. However, this is always have to be careful. A good example is the beef. Because beef, we talk about E. coli 157H7, Shigella toxin producing E. coli, the safety concern. But at the same time, we all care about is juiciness, flavor, and tenderization. So the conservative of the operational limits, a conservative value, really need thinking about is the quality. Second is avoid the deviation from a critical limit. Let's say a low acid food. FDA regulation pH at 4.6. We could set up a low level, a more conservative operational limits, pH 4.0. That makes sure the 4.6 is absolutely you reach that level. Another one is for process variability. So for example, my temperature, the target critical limits is 71 degrees Celsius. I find my cooking machine is variable sometimes, cannot reach exactly 71. Sometimes 71.5, sometimes 71.2, it's hanging around there. So I would love to set up a little bit higher, maybe 71.5 degrees Celsius. Then it will be, make sure it is working. So here you can see what happened. This is a really good picture. X-axis is the time, Y-axis is the temperature. You have this red line for critical limits. You have this dotted line for operational limit. So what you're going to see, if you are temperature above operational limits, of course, you don't need to do anything. You don't have to worry about that. But once you see your temperature is below operational limit, but above critical limits, you may need to do some adjustment to prevent deviation. However, your product is still good. You don't need to initiate corrective actions. However, if you see the temperature is below critical limits, that means you have to initiate corrective actions. The product have to be loaded. food safety plan may have to reevaluate. We may need to see how to treat those affected products. So this is a very nice figure to showing that. So you can see here the corrective action is required. So we gradually fill this table until here we go to corrective action. So what they do, they are talking about is hold the product back to the last good check and evaluate, rework, discard or release, determine the root cause reason why it is not appropriate. So we left these two. This is not talk about that because this is in chapter 13 and 14 later on. Summary. So what we are talking about so far? We are talking about critical control points, how we control it. The procedures must be documented. For the process-related hazards requiring a preventive control identified through the hazard analysis process. For each analysis, for each process-related preventive control identified, we need to make sure the parameters, the values referred as critical limits is met. The monitoring procedures including what, how, frequency, and who did it. Corrective actions has been identified. If there is a failure or deviation happens, then you need to initiate corrective actions. Verification and the records is established. This will be discussed later. So finally, I would love to appreciate the McGill University and the Institute for the Advancement of Food and Nutrition Sciences to invite me here to give the talk. And this talk is also sponsored by NIFA Hatch program. And I mentioned earlier, sponsored by Critical Agriculture Research and Extension and USDA NIFA Education Workforce Development Program. And I also would love to thank all the students in my lab. They work in the lab every day and they supported our great land-grant university mission, which is teaching, research, and obviously today we talk about is outreach and extension. So thank you very much, and I believe we have a follow-up discussion later on.
Thank you, Dr. Shen. Looks like we have a few minutes, about 5 minutes left for questions specific to your talk. Let me go ahead and pull up here. So there's been a lot of talk in the news about new novel foods. I'm thinking cell cultured meats, things along that line. So how do these HACCP principles apply to those new novel products?
I would say that for those new novel products, we need to first of all identify is the hazards. So identify those hazards, especially for the biological hazards like pathogens. Definitely need to do is a predictive model to see those pathogens survive in those products. So certainly in the lab work, we need to have those sample to inoculate with the bacteria, do a different packaging, storage in different temperature, then to see the growth curve. Another thing is that most of these plant-based products, they are depends on their water amount. So the moisture amount usually is very high. So I would expect them, they could be favorable for the bacteria to grow. And also the extruded protein from those surfaces, it could be also a concern for the bacteria to use. So each of those plant-based products, I do believe the HACCP plan and also the process preventive plan has to be developed individually based on the more scientific research to do. So, but we could use some of the already existing documents in the website. In the FDA website, they have like a lot of modules, and the FSIS website have lots of modules talk about HACCP plans. The original one we could use, but we more importantly is do individual validation studies, especially shelf life and challenge studies to see the passion there. And I think that's important. This need to collaborate with a microbiologist and the quality assurance person, even the mathematics person, because some of the models may be different from the old one.
Okay, interesting. Kind of following the same line, how are artificial intelligence technologies being used to improve food safety in the supply chain in line with HACCP procedures?
I would say that based on the my knowledge is that they have a lots of the work, research work has been done that. So if you go to International Association of Food Protection Conference, IFT, Institute for Technology Conference, you see lots of the lab work has been doing, and the machinery has been established, the database it has been developed, and lots of the work has been done, but I haven't seen anything really applicable at this moment in the local level, in the local community. But I believe the large industry has started to look for something. So there will be a very bright future for the people working that. So myself was being interested about is some of the robot. So for example, we are using a traditional spray system to the decontamination foodborne pathogen on the surfaces. We do the garden spray, conventional spray, and also using electrostatic spray. But I was thinking about if there is some of the robot, the AI person could do that. That certainly will save a lot of the labor work. It's going to be more uniform. And it's also going to be an interesting topic for the students to learn, because they bring their science mind, which is not only the microbiology, they bring their like physics, chemistry, math idea. It's a very interesting topic. There's integrated, we talk about integrated education, research, and outreach. So those are the works we can be done. And also how we going to apply those technology into the local community. That is also a challenge, because certainly those new technology has been using, but the cost, the installation, and it will be always a challenge. So I think it's have a very bright future. I see lots of our co-workers have been doing that. I see our previous speakers, Dr. Lu, Dr. Hu, and Dr. Dr. Ro, Dr. Ma, their groups has been doing those fabulous machine learning studies. So I'm looking forward to see those more and more coming.
Yeah, I think we'll definitely see a lot more research in that area in the coming months, if not years. All right. Awesome. Well, I appreciate your time, Dr. Shen. We're just going to take a bit of a brief break here before we bring all of our speakers from the workshop back for a final discussion. So I just want to take this opportunity to say again, thank you, Dr. Shen, for that great presentation. And we will reconvene everyone at 3:30.
Thank you very much.